This is an example of hard level or level 3 problems in the Laplace Transforms game in Circuit Tutor. So as always, we have examples available at all the different levels of difficulty. We could look at a hard level example for example, and that would be a problem of this type where we have constant times a decaying exponential multiplied by a cosine function and the unit step function, and it will then show all the details involved in applying the formula. And of course there's a link always to the Laplace Transforms table there if you want to refer to that. So that is available. If you have any difficulty with the exercises, it would be a great idea to look at some examples. Okay, there's also user-selected examples available in this particular game, and that's where you choose a particular type of function for which you want to see an example of a Laplace transform being computed. And you can also make that a time-shifted function if you wish by checking that. So let's go back to the game, and we'll start a hard-level problem. So this time we have a constant of -11 multiplying a decaying exponential and a cosine function. In this case, cosine of 6t, multiplying, of course, the unit step function, which is virtually always present in these problems because that's required for Laplace transforms. Okay, so first of all, we will probably need the table, unless you can happen to remember those. So that's available right here in this link. But if we click that link normally, it's going to come up as a new tab in the browser, which might not be super convenient because then you can't look at this at the same time you're doing the exercise. So what I'm going to recommend instead is that you may want to right-click on this and choose Open Link in New Window. That way we can get a new browser window with the table. And now we can reduce the size of that, move it over here, and then also go back here and reduce the size of this so we can set them side by side. And that makes it a little bit more convenient to use the table as we're actually doing the exercise. Okay, so now let's look at this. It's again a constant times a this function. And by the way, the constant multiplication, that basically will just use the linearity property of Laplace transforms. Remember that if you multiply a function in the time domain by a constant, that corresponds to multiplying the Laplace transform by the same constant. And that's just based on the definition of Laplace transforms in terms of integrals. As we know, integrals are linear with respect to that type of thing. So, and if you weren't sure about that, you could always bring up Laplace transform properties, but linearity is something so basic that you should be familiar with it. Okay, and by the way, if you do need trigonometric identities, they are also available on this link here. Okay, so let's look up what we need here. We need a decaying exponential times a cosine function of just a simple argument. So we find that here. And so we see that that's going to have the form s plus a over the quantity s plus a squared plus omega squared. So now we'll go and enter this. Notice that we have a template-based equation entry system, similar to what you did in the downloadable software. There are 3 tabs of terms here, and we have to pay attention always to what we're being asked to do. So this, of course, is to find a Laplace transform, which obviously will be in the Laplace or S domain. It will not be in the time domain. So therefore, any of these terms that involve time, the t variable, are going to be useless to us right now, as would these, which involve t minus t naught, the time-shifted thing. So we need to be sure to go onto the tab for Laplace domain in order to find the correct terms that we will need to actually construct a Laplace transform. So it's always important to make sure what you know what the problem is asking for. Okay, so as we see here, we're going to need a ratio. So we'll use the fraction template to begin with. And you can either drag this into place, or you can just click on it and place it that way. If you ever do place something here you don't want, like for example, if I put that in there and I'll decide it, I guess that's actually not allowed in a fraction block. But if I put it there and I decide I don't want that, then I just drag it out. Okay, and so we have our fraction template there, and so we need the s plus a quantity squared in the denominator. So I'll bring this term down there, which will have that form. There's a direct thing that has that thing. And the a would be the coefficient of t in the decaying exponential as per the original template here. So that's just going to be 1 in this case. So the a is going to be 1, and then this is supposed to be squared. So we fill in the squared in that text box. And then we need to add to that the omega squared, which is basically just a constant. So we're going to add a plus sign and a constant, a real constant specifically. And our constant is going to be the omega squared. And remember, omega, by definition, is what multiplies the t in the argument of the cosine. So that's going to be 6 here. So 6 squared, of course, is 36. So we just enter that there. And then in the numerator here, we're going to need s plus a. So we'll put that into place here. The a, again, is 1, just like it was in the denominator there. So we'll fill that in. Now, we do, however, have to have this factor of the negative 11. So we'll bring another constant down here. And actually, I think I'll just move this over before. And we'll put negative 11 there. And so that should complete what we need for this particular problem. So now we'll just, and of course, if you ever need to give up, for some reason you can't find the answer, you can just click this button. And as always in Circuit Tutor, there is no penalty for giving up. You'll simply be given another problem of the same type after they show you the detailed solution to this one. And of course, we can also use the clear equation button if we ever mess up the equation so badly that you want to start over. Okay, so we'll just click check equation. That is correct. And if necessary, you can also view a detailed solution of this by clicking this button, and that will show you all the steps that were involved, similar to what you would see in an example. Okay, so let's do a second problem now at the hard level to show you an example of a little bit different problem. Okay, so this time we are going to have a decaying exponential, a constant of -1, multiplying it, and this time it's a sine function, but in this case we have a phase shift in the sine function as well as the unit step function. So we're going to need a different formula over here. So we can check that, and that will be this formula down here, matches the type of term we're using. And again, the derivations of all these were covered in the introductory tutorial if you had any question about how this is derived from the integral definition. Okay, so we need this type of function. So we're going to have s plus a sine phi, where phi, again, is the angle that's being added, and that is going to be just plus 30 in this case. There's no minus sign here. If there were a minus sign, then, for example, if it said minus 30, that would mean phi is negative 30. So we have to be very careful about the signs. Okay, then that's going to be plus omega cosine phi, and then s plus a quantity squared plus omega squared. So let's do the denominator first. So again, we don't want to be in the time domain here. We need to go to the Laplace domain. And so for the s, first we'll put in the fraction template here, and then we'll put in the s plus a squared, and we'll fill in a 2 there to make that squared. The a, again, will be the coefficient of the negative t in the exponential, so that's going to be 6. And then we need to add to that the omega squared, which is basically just a constant. So we'll put in a plus sign here next to this, and a constant. In this case, just a real constant is all we need. And that real constant will be the omega squared. Remember, omega is the coefficient of the t in the argument of the sine function, as you see in the table. And so that's going to be 5 squared. So 5 squared would be 25 that we enter in here. Okay, so that does the denominator, and then we need an s plus a factor here in the numerator. And the a, again, will be 6, as it was in the denominator. Again, that's the coefficient of the negative t here. So we have s plus a, and then there's going to be a constant multiplying that. So I'll bring a constant in front of it. Try that again. Okay, and that's going to be sine of phi, but then we also need to multiply it by -1 because we have a multiplicative constant here of -1 in front. So sine of phi, our phi, remember, is 30 degrees. So you may know that value offhand, but if not, we can always pull up a calculator and just do sine of phi. So sine of 30 degrees. And notice that I do check, of course, that I am in degree mode here in the calculator. If not, you could go into mode and adjust that here to be in the appropriate mode, but you'd always want to make sure you are in the correct mode before doing this, obviously. And so sine of phi, and then and actually well, we want this all times -1, so I'll just go times -1. So that will give us a -0.5, as you may have known is the answer. And so we have -0.5. And then the second part is going to be plus omega cosine phi. And again, we also have to multiply times the -1. So the cosine of that phi, again, you may know that value, but if not, we can always pull up the calculator here. So cosine of 30 and that's still times -1. And we also need to multiply by, in this case, the value of omega. And remember, omega is 5. So we'll also multiply times the 5. And so that'll give us -4.33. And so we will go ahead here and just enter that as another, so it's -4.33, so I'll put a minus sign here and another constant and fill that in as the 4.33. Okay, so now we can go ahead and check that answer. That should be correct. And it is. And once again, we can get a detailed solution, if necessary, by clicking here, just to review how the work was done. So that does complete the hard level problems.